Hi, everybody. My name is Matt. I'm a third-year PhD student at ICRA UWA, and I'll be talking to you about collisional relaxation and how that affects morphology and kinematics in simulated galaxies. I've given the talk the subtitle, "What do you need to know about collisional heat?" As is tradition, I'd like to start my simulation talk by talking about real galaxies. So here's a selection of just 8 edge-on super thin disks. Well, on the left-hand side, I've got a bunch of super thin disks. On the right-hand side, I've got some disks that have been puffed up for one reason or another. The main point of showing you all this is that, this is basically the goal. We want our simulations to be able to reproduce galaxies that look like this. So you need both the really thin things and the things that are puffed up. How are our best simulations doing in this respect? The answer is not all that well. So here's just a sample of 4 cosmological simulations that are really well studied that people are using to look at morphology over the course of the universe, and they just aren't reproducing these super thin galaxy disks. And that's just what they look visually. It might be even more concerning if you look at the statistics. So here's plots in the TNG 50 simulation paper. So it's the probability distribution of galaxy disk heights in a particular mass range. The thick red line is for the highest resolution TNG 50 run they did, and the thinner red lines are a factor of 8 worse resolution. The fact that they're just not on top of each other means it's by definition disk heights are not converged in these simulations. So what do we think is going on? I promise this is my only slide of text. But from theory, both the dark matter and stars should be effectively collisionless. I'm just flashing up a bit of a schematic of a 2-particle gravitational interaction. You'll notice the deflection angle, for small angles anyway, is about proportional to the mass of the particles involved. The particles in our TNG 50, which is a relatively high resolution simulation when it comes to cosmological simulations, is on the order of 100,000 solar masses. So this does cause the dynamics to change. One way to think about it is that individual orbits of stars, from one collision, are perturbed, so they're not as circular as they once were. And these perturbations happen at all length scales. So you can't actually just increase the Hawking length to remove this sort of effect. Another way to think of this is that if you have a dark matter halo resolved with fewer particles than you otherwise would have, the potential is just not smooth. So if you try to integrate an orbit around a lumpy potential, it's not going to stay circular as it should. And for disks, it turns out you want all the stars to be on nearly circular, almost homogeneous orbits. So the fact that they are being perturbed by this effect is what we think is causing the galaxies to be less disky than they otherwise would be. The particles are exchanging energy, and we'd like to run some experiments to find out how much energy is being exchanged and what effects we can expect in our cosmological simulations. That's where we turn to some really specialized control simulations. All we've done is set up an exponential disk in a Hernquist dark matter halo. We've resolved it with a whole bunch of different numbers of dark matter particles or mass resolutions, and just let them evolve. There's no stellar evolution, there's no external galaxies. And you can see along the top row here, I've got just the initial conditions. You can see it's a super thin, super flat disk. And after 5 gig years, on the left-hand side, for our highest resolution galaxy, it still puffs up a little bit, but it's nowhere near comparable to the middle or the one on the left, which is the lowest resolution resolution simulation that we ran, where by 5 gig years, the disk is just not recognizable anymore. yeah, going from just images to something more statistical, we can look at the galaxy shape. So I'm showing where you draw the 3D axes for two common items, a frisbee and the galaxy. And I'm using like the axis ratio between the major and the minor axis to quantify how the distribution of the positions of the particles has evolved. So I've got like a bunch of colors there, which are a bunch of different runs that we did with different resolutions. Along the bottom is our highest resolution run where it starts off super thin and it stays super thin throughout the entire time, but it does evolve a bit. Our lowest resolution galaxy, on the other hand, the top one in blue, starts off super flat and then becomes almost spherical by the end.
Sorry to interrupt you. In my world, the frisbee is oblate.
Oh no. Yep, you're right. I think I've made a copy paste error somewhere. Oh well. Yeah, so that's the positions of the particles. How about the kinematics? Turns out the kinematics are also completely perturbed as well. So here I'm showing the time evolution of V over sigma. For our galaxies, again, the purple one starts off super high, highly rotationally supported, whereas our lowest resolution run quickly, like just over 3 gigayears, like drops below the threshold of like 1 V over sigma and is dispersion supported by the end of our simulation. Yeah, again, just reiterate, there should be no evolution because the particles should be collisionless, but we are observing this. Also, we spent a lot of effort into producing a model for how the kinematics are evolving, and that's what I'm showing in the dashed lines here. So these are our measurements. We can play the opposite game now. So given a model for how the kinematics evolve, what particle mass resolution or how many particles would you need if you wanted to resolve galaxies to a particular kinematic resolution? That's what I'm showing in this plot, where I have the y-axis V over sigma, and on the x-axis the number of dark matter particles that I'm assuming. So what I've done here is I've started at time equals 0, like a galaxy as a pure disk, so no dispersion at all. So technically the initial V over sigma is infinity, and then just let it evolve for the amount of time that I'm showing in the different colors. And according to our models. And like these are results for what you expect the maximum possible V over sigma for a galaxy to be if it started from a pure disk. Cool. Along the top, I've got the equivalent like halo mass of an Eagle galaxy. And if you're looking at something like Milky Way mass around 10 to the 12, if it's a really old system, you're just not going to be able to see any disky structure left over because it would be destroyed by collisional heating, basically, is the takeaway from this plot. And just to lead into the next talk a little bit, angular momentum also is affected by collisional heating. It's not quite the same simulations we've run here. Like we've got a fixed stellar to halo baryonic mass fraction in the runs that I'm showing here, and like I just to resolve them with the same dark matter particle mass. So this is kind of what you'd get if you looked at the like full relation for a particular simulation that has the same dark matter, where all the galaxies have the same particle masses. As you can see, once you're at high enough resolution, you don't have to worry too much about collisional heating, but like definitely if you're going down to low numbers of particles, it starts to affect your results a lot. And the stellar angular momentum ends up being transferred to the dark matter when it really should not be. So in conclusion, disk galaxies have always been a challenge to simulate. This is just like the next thing on the list that we have to take care of. Fortunately though, collisional heating is mitigated if we just move to high enough resolutions. And now with our models, we know exactly what to expect in the future. Thanks.